Ladies and gentlemen, welcome to this SEAM seminar. It is traditional in Australian and New Zealand culture to have a welcome to country. We respectfully acknowledge the Wurundjeri people and their elders past and present, who are the traditional owners of the land on which Swinburne's Australian campuses are located in Melbourne's east and outer east. We are honoured to recognise our connection to Wurundjeri country, history, culture and spirituality through these locations, and strive to ensure that we operate in a manner that respects and honours the elders and ancestors of these lands. We acknowledge the traditional owners of lands across Australia, their elders, ancestors, cultures and heritage. My name is Chris Burnt. I'm the Director of SEAM, and it's my pleasure to dedicate and acknowledge this series to the healthcare staff and essential service personnel who have demonstrated their commitment and self-sacrifice. They are working at the front line of the 2020 global pandemic during a crucial time of need. Their devotion and dedication is inspirational. We're all stronger when we work together. Thank you. Today's seminar will be given by Professor Dr. Rogerio S. Lima from the National Research Council in Canada, who will be talking about understanding how much thermally sprayed thermal barrier coatings protect jet engines against major failure. He has decided to give a wonderful tutorial presentation. Professor Dr. Rogerio Lima has worked for some 20 years as a research officer at National Research Council of Canada. He is a graduate of Stony Brook University in New York, USA. He is also an adjunct professor of Concordia University in wonderful Montreal, Canada, as well as being an associate investigator with SEAM. He speaks 4 languages fluently: English, French, Portuguese, and Spanish. He is also the new Vice President of the Thermal Spray Society of ASM International. We're absolutely delighted to have Professor Dr. Rogerio S. Lima give this talk. Over to you, Rogerio.
Thank you very much, Dr. Burn, for this great opportunity. So, Amanda, I participated in the MICE 2020 February in Australia. It was a very good seminar, a very good conference. And I'm very, very happy to be present again among the SEAM researchers and SEAM students. And I guess, for example, may have people from different parts of the world right now. Even my brother maybe seeing me right now. Hi, Daniel. Okay, yeah, maybe you are there. So thank you very much for this invitation. I do appreciate the opportunity. And today, so as Professor Burns was saying, I'm going to give you a tutorial presentation on thermally sprayed TBCs for jet engines. So basically, curiosities about thermally sprayed thermal barrier coatings, or TBCs. So it's one of the main critical components of the aircraft. So TBCs basically they are less than 1 millimeter thick, and they are located in the static cross sections of the turbine, like for example, combustion chambers, vanes, and afterburners. And basically, TBCs impede the catastrophic failure of the turbine engine. So when you are flying, mainly when we're taking off, the combustion temperature inside the combustion chamber is higher. The temperature is higher than the melting point of the metal that is surrounding the combustion chamber. And therefore, for example, that coating, that thin little coating, less than 1 millimeter thick, is protecting you against a major disaster. So this presentation showing in very simple terms how TBCs work. And basically, I'm going to concentrate the presentation on combustion chambers, on TBCs for combustion chambers. But before we go there, you need to basically understand how jet turbines work. And you're going to have a tutorial movie, 1 minute and 30 seconds to show you, for example, the basics of jet engines. Jet engines 101, let's see how it works. Let's go there.
The engine pulls air around the engine and sucks air into the core. We'll come back to that outside air in a moment. For now, let's follow the air in the core. It goes into a compressor, something like many household fans joined together. Each fan gets smaller and smaller as the blades squeeze the air into a tighter and tighter space, compressing the air like you would squeeze a balloon, until that squeezed air is mixed with jet fuel, a kind of super gasoline. In the combustor, that air and fuel mixture meets a flame and shoots out the back of the engine. The rush of hot air spins a turbine. The turbine is like a windmill that scoops up energy from the heated air and spins the shaft connected to the fan at the front of the engine. The excess hot air from the combustor blows out the back of the engine, producing thrust. Remember that air rushing outside the engine core? Together, the turbine and fan push a larger mass of air than the core ever can, for much more thrust.
So, as you saw in this video, basically you have the turbine engine, and you have two sources of thrust, the core thrust, and you have the fan thrust. But in order to have the thrust, basically you need, the combustion of the fuel inside the combustion chamber, right? And there we need the TBC. So let's see, for example, the combustion chamber in more details. So this is the turbine, you can see the combustion chamber, and this is how a combustion chamber looks like. It's called an annular combustion chamber. And basically this combustion chamber has three main parts. Okay, you have the outer liner, you have the inner liner, and you have the dome. And here, for example, this whitish region here, okay, inside the combustion chamber is the ceramic TBC. So by looking at it, some of you may not understand very well how the combustion chamber looks like. But if I'm going to show you this, so a combustion chamber on an airplane looks like, okay, basically a cake pan. Okay, so basically here you have the outer liner, here you have the inner liner, and here you have the dome. So if you understand a cake pan, you can understand, for example, how a combustion chamber or a turbine looks like. Okay, so, well, curiosities about the combustion chambers and TBC, so the state-of-the-art architecture of combustion chambers for of TBCs for combustion chambers. Basically, to have an idea, the combustion chamber wall thickness is only 1 to 2 millimeters thick. So when you are flying, for example, this thickness here is about 1.5 millimeters. So when you're flying the combustion chamber, the metal, the nickel-based alloy has a thickness of only about 1 to 2 millimeters thick. And you are burning the fuel in high power. Basically, the temperature is higher than the melting point of the material. So it's amazing, isn't it? And here, for example, over the combustion chamber wall, you have a bond coat. It's basically a nickel-based alloy. The thickness varies from about 100 to 200 microns. And this coating here protects the combustion chamber wall against high temperature oxidation. And here, for example, over the bond coat, we have our ceramic TBC. Okay, the standard material we use today is basically the zirconia yttria, the standard materials for the ceramic TBC. And the acronym is YSZ. So in my presentation, I'm going to say the acronym YSZ many times. It's the zirconia yttria, the material of the TBC. And basically the composite or the thickness, okay, varies from 250 to 500 microns. And the porosity of that ceramic TBC varies from 10 to 20%. And the thermal conductivity from 0.7 to 1 watt meter Kelvin. And just to have an idea, the melting point of this material is 2,700 degrees Celsius, while the melting point of the nickel-based alloys is between 1,300 and 1,400 degrees Celsius. So we need to have a very high temperature material to allow to have a very high combustion temperature. And talking about combustion temperature, we know from the film that you have the heat generated by the combustion. And what is the maximum limit that TBCs are working right now? The maximum limit is about 1,300 degrees Celsius, okay, that these TBCs are seeing right now. And in the turbine engine, in the back, okay, of the combustion chamber, part of the air of the compressor basically is bypassed. and it's cooling the back of the combustion chamber wall, and the maximum temperature of this wall right now is about 1,000 degrees Celsius. And for example, as you have 1,300 degrees Celsius in here and 1,000 in here, you have basically the gradient. You have a temperature drop. You have the famous delta T. Well, basically, I mean, what you're going to learn for my presentation today. So we're going to learn some important points, like, for example, why the maximum temperature limit of the TBC is 1,300 degrees Celsius. We're going to understand why the maximum temperature of nickel-based alloys is about 1,000 degrees Celsius. And you're going to understand why the minimum limit of the TBC is 250, and the maximum is 500. And also, for example, we're going to see what are the temperature drops that you have along the TBC system. Is it 100 degrees Celsius, 300 degrees Celsius, 400? So by the end of my presentation, if you can understand everything, you're going to have a knowledge of the system. So help me God, right? So before I continue, for example, my presentation, some of you, for example, are asking this question. I mean, how can I spray a TBC inside here my cake pan, right? So we're going to see a new movie right now, and it's going to show you a unused combustion chamber that's going to be overhauled. So the combustion chamber is going to be disassembled, the TBC is going to be stripped off, a new TBC is going to be sprayed again, the combustion chamber is going to be reassembled and shipped back to the client. We're going to see it right now. So very cool, eh? Okay, the difference between a combustion chamber before overhauling and after overhauling. But, for example, why TBCs are paramount in turbine engines? So this is the question, one of the questions I need to answer to you right now. As you know, I have been telling you that the maximum temperature that the walls of the combustion chamber or nickel-based alloys can withstand is about 1,000 degrees Celsius. And why it's 1,000 degrees Celsius? So here you can see this graph where you have the onset stress for permanent deformation, or the yield strength, the correct name, and this is the temperature, and these are the different types of nickel-based alloys that are used in turbine engines. And many of you know, for example, the concept of yield strength. And I'm going to have, for example, a demonstration here with a can of a beer, right? So imagine, for example, I have here the can and I'm going to apply force. Okay, you can see, for example, I can deform elastically the can, and when I release the force, basically the can goes back to its original position. So I am working below, okay, under the yield strength of the material. However, if I apply enough force, basically I'm going to deform elastically, okay, the metal of the can, and therefore I went over the yield strength of the material. So basically, you do not want to have a combustion chamber that's going to be in this way, right? So above the elastic point. And therefore, as you can see in this graph, you can notice that by about 1,000 degrees Celsius, you are very, very close to the limit of a kind of catastrophic failure. And to make a long story short, this is the time where structural engineers are crapping their pants. Okay, so when we're close to 1,000 degrees Celsius, the structural engineers, they say, don't go over 1,000 degrees Celsius. And basically, in a simplified way, that's why, for example, the limit of this material is about 1,000 degrees Celsius today. And you can try to understand. No, for example, I have been telling you that the maximum temperature limit of TBCs today is about 1,300 degrees Celsius, right? So imagine if you try to use 1,300 degrees Celsius in here, okay? In very good English, you're going to say, Houston, we have a problem. It's going to be a disaster. And that's why, for example, without TBCs, we're going to have a catastrophic failure of the engine in flight. Based on that, some of you are going to ask, so why we have to operate at 1,300? Okay, we can keep operating turbines at 1,000 degrees Celsius, don't need TBCs, and we're still in the safe region of the metallic alloys of turbine engines. So why you don't do that? It's not as simple as that, and we're going to understand why in the next slide. Okay, so why we need to keep increasing the combustion temperature of turbine engines? And if you see this graph, you can see here the turbine-specific core power versus the turbine inlet temperature. What is turbine inlet temperature? Turbine inlet temperature, this is the turbine, this is the temperature of the gases when they get out of the turbine and they enter here the blade region. So this is basically turbine inlet temperature. And you can see that in between 900 degrees Celsius and 1,700 degrees Celsius, this relationship is linear. And why is that? It's very simple. The higher the temperature of the gas inside the combustion chamber, the higher the expansion of the gases, and therefore the greater the efficiency of the engine. That's all. And you are talking about airplanes. We need lift. So we're making larger and larger airplanes, and we need better and better engines to lift off that big weight. Therefore, for example, you need to keep increasing the combustion temperature. And some of you are going to say, okay, now I understand why we need to work at 1,300. But why would not work at 1,400, 1,500, 1,600? Because I can see the graph here is much better. Well, I say that. So why we are limited to 1,300 in TBCs, the temperature? And basically, the YZ TBCs, they start to degrade slowly when the temperature is higher than 1,300 degrees Celsius. So you have a diverse chemical reactions, you have phase transformations, sintering, stiffening, and it leads to the failure of the TBCs. And that's why, for example, we are limited to this value of 1,300 degrees Celsius right now. So based on that, some of you are thinking, so how can we simulate this environment? Because we need to study these TBCs, right? How can you simulate this thermal gradients within TBCs? Well, there are different types of systems you can use. And for example, it's called the laser rig. So the NRC has one. It's a system to generate, to simulate this thermal gradient. And it looks like this system in here. Okay, so basically you have a substrate, a puck-shaped substrate. You have a 25 millimeters in diameter, 3.2 millimeters in thickness, and we insert a thermocouple inside here, the substrate, and here you coat what TBC. So this guy in here, it's this guy in here, it's this guy in here. So for example, we have here, for example, the TBC, and you put in the rig, and in the rig we have a laser, and the laser, he shines on the sample, an infrared laser, and it heats up the sample. And you can see in this movie right now, you can see, for example, we have the sample here coated with TBC, and when you apply the infrared laser, basically you heat up, okay, the system will generate high temperature, will simulate this part here with thermal gradient. And here, when you look at this picture, you can see here there is a nozzle in here. This nozzle will have compressed air at room temperature that keeps flowing over the backside of the substrate. And this backflow on the backside of the substrate basically starts to cool the system. And therefore, by doing this, we generate a thermal gradient and we can study TBCs. And basically how we study them, we measure the temperature of the YZ or ceramic TBC using a parameter, and you measure the temperature of the substrate using this thermocouple here. And this distance here is about 1.6 millimeters. And I have been telling you that the thickness of these walls are between 1 to 2 millimeters. So if we're measuring the temperature at 1.6 millimeters, are basically the average of the thickness of these combustion chamber walls. So it's a good representation of the real system. So, but how can we maintain the thermal gradient in the laser rig? Okay, so you know you have to generate the heat and you have to generate the cooling. So what we do, basically we have a constant back cooling at room temperature. We have this nozzle here, okay, so we have compressed air, room temperature is cooling all the time. And the laser here, basically we tell the system, okay, It's a computer-controlled system with a laser rig. Laser rig, please keep this temperature of the YZ-TBC at 1,300 degrees Celsius. So basically, based on the measurements via the pyrometer, the laser rig is going to adjust its power to keep this temperature at 1,300 degrees Celsius. And this way, we are going to generate a thermal gradient. So if we make a good TBC and you put the TBC in the laser rig, so if the TBC is well engineered, okay, the substrate temperature should not be higher than 1,000 degrees Celsius. It's the maximum the temperature that the substrate can handle. So in order to do this, okay, to test the TBC, we also have to make the TBC. So this is, for example, our standard TBC or benchmark TBC that we created in NRC. So we're going to use a plasma spray torch to make the TBC. And as you know, okay, I have been telling you that the minimum limit or the minimum thickness is about 250 microns, and the maximum limit is about 500 microns. So initially, I'm going to make a thinner TBC. It has a thickness of about 260, right? And then you have to make the same TBC but thicker. Okay, so make another one that's thicker. It's about 460, almost at the upper limit in here. And I have been telling you that the porosity of these TBCs are in between 10 to 20%. And the porosity of our TBC is 15%. So we are inside the limit. And also have been telling you that the thermal conductivity of these TBCs is between 0.7 to 1 watt meters per Kelvin. And the thermal conductivity of this TBC is 0.8. So we're right at the good point of having a representative TBC. And right now we have to get this TBCs 250, 260, and 460 and put it in the laser rig. So let's see how it behaves. So let's see, for example, what happens when the thickness of the TBC is 260. And this temperature should be around 1,300. This temperature here cannot be higher than 1,000 degrees Celsius. Let's see if we can achieve that. And this is the graph. Okay, so during 6 hours continuous non-stop, we were able to keep the temperature of the YZ above around 1,300 degrees Celsius, this limit here. Okay, and we were able to keep the temperature of the substrate around 1,000 degrees Celsius with this limit in here. So it's okay. So we can see the delta T that we create in the laboratory is 280 degrees Celsius. So this is the TBC really working. Okay, because I mean, at this temperature, if we didn't have the TBC, this matter would be just a goo. Okay, so this is really the TBC working. As you can see, for example, if the minimum thickness of the TBC or the YZ-TBC is 250, the limit or the maximum limit of 1,000 degrees Celsius is respected. It means that the aircraft is safe to fly. But also, for example, you can imagine if the thickness instead of 260, it was, for example, 160. So in this case, you can foresee that the temperature on the substrate would be much higher than 1,000 degrees Celsius, and therefore the system is going, would fail. And this is the reason why you need to have a thickness of at least 250 to guarantee that the temperature of the substrate will be about 1,000 degrees Celsius. Okay. So if the thickness of TBC is less than 250, like 150 degrees, 150 microns, basically the limit is not going to be respected and the aircraft is not safe to fly. Let's see what happens in the other way. So here, for example, I'm going to put the other extreme to 460 micron thick TBC. Okay, so this temperature here should be around 1,300 degrees Celsius. And the temperature here cannot go over 1,000 degrees Celsius. Let's see how it works. You can see the graph. So we performed the experiment for 6 hours, okay? So, and we did it. So the temperature over the surface of the TBC was about 1,300 degrees Celsius, right there. And the temperature of the substrate was about 844. So we have a gradient of 460 degrees Celsius. So you have a much thicker coating, right? So if the maximum thickness of the TBC is about 500 degrees Celsius, the maximum substrate limit or temperature of 1,000 degrees Celsius is also respected. And so aircraft is safe to fly. And of course, that we can say For these TBCs, a thickness between 400 and 500 microns are preferred, because basically we put the substrate at a very comfortable limit. We're well below the limit of 1000 degrees Celsius. And that's why, for example, these thicknesses are preferred. And based on that, you can say why we're not using an 800 micron thick coating. Because I mean that even at about 460, we're really protecting the substrate. And if you try to put a much thicker coating like 800 microns, you are basically adding weight to the turbine, and you do not want to do this. So when you have a PVC in which the thickness is about 400 to 500 microns, you have an enhanced safety limit. And it means that the engine on wing is going, so the TBC or the turbine is going to be on the wing for a long time. And this is really, really important. And why? For example, I'm going to show a concept called hot section inspection. So basically, when you go for a doctor, okay, for a kind of your annual checkup, basically the doctor is going to ask for a blood test, right? So this is a standard test. And the blood test, okay, so for a turbine, so when a turbine goes to the mechanic, is the hot section inspection. Basically, we are going to use a boroscope, okay, and analyze to see if the TBC is still there. So we're going to use a boroscope and we're going to look at the TBCs. So if the TBCs are still there, it means that the engine keeps flying. So it's a good engine, it can keep flying. It's the same thing, for example, if you go to the doctor, you have your blood test. If your blood test is good, the doctor says, okay, that you are okay, go back in the next year. However, for example, if the TBC shows signs of expiration, okay, so the engine needs to be repaired. It means this is not good because the engine needs to stop flying. And just to have an idea, I'm going to show you this video here, okay, of the combustion chamber, our, okay, cake pan being analyzed via boroscope. Here in the section, you have the TBCs. So as you can see from the video, basically the TBC is intact. There is no signs of expiration. It means that this engine is going to start flying again. And it's important is, for example, because that if a turbine is going to fail, basically it's probably going to start failing at the TBCs. Why? Because this is the region where you have the highest temperature and highest stresses in the engine. And that's why, for example, it's very, very important for companies to keep analyzing the TBCs. So it means that the better the TBC, the longer the time between overhauls. So the time between overhauls, the TBO, is basically how many hours a turbine can run without having to pass by an overhaul. And the quality of the TBC is very, very important to keep improving the TBO. And based on that, how long these turbines can fly? Okay, it's a good question. So I'm going to show you some examples. For example, the Pratt & Whitney Canada PT6 series, okay, that powers aircraft like the Havilland Canada Twin Otter and the Bell Canada Griffon, is going to fly for 6,000 hours. It's not a guarantee, but basically this is the type of limit that the company gives to the engine. So how about, for example, the Pratt & Whitney Canada 100 series? That powers like aircraft like the Viking Canadair and the Havilland Canada -8. So it's 8,000 hours flying in good conditions, okay? So it's a good amount of time. And the Pratt & Whitney Canada 800 series that powers the Dassault Falcon X. So, and also, for example, this engine is considered to be the upgrade for the Boeing B-52. It's 10,000 hours of flight. And how about, for example, the big guys? Just like the G90 series, okay, that powers these big aircrafts like the Boeing 777. It's 20,000 hours of flight. It's amazing, TBO, right? It's huge. And how about fighter jets? So like the Saab Gripen E, so it's a very modern engine, the GF 414, it's 6,000 hours. So it's not too much because basically fighter jet engines are always operating at the limit. That's why they typically they do not last a lot. So as I was telling you, okay, to have a good TBC is very, very important to increase the time between overhauls of an engine. And sometimes, for example, so you have the inspection here, the boroscope you saw in the movie, and you have zones of expallation, tiny zones of TBC expallation. You need to remove the combustion chamber from the engine. Okay, it means that the aircraft is not going to fly, so we have to remove the combustion chamber, we have to ship, and the combustion chamber has to be resprayed and shipped back to the client. It takes a lot of time. And that's why, for example, some companies right now are thinking about, okay, how is it possible to try to repair, okay, a TBC, I suppose some little zones of installation with TBC in loco on, when the turbine is on wing. So without taking the combustion chamber off the turbine, it means that you have to do a thermal spray on a tiny little torch in a very, very localized zone, okay? And for many thermal sprays, they think it's mission impossible, right? So let's see if it is really mission impossible. Let's see how we may be able to do this in this movie. So, that Rolls-Royce is trying to do this for sure. For example, is something, amazing. So, end-to-end, basically, final comments. Thermal spray TBCs are paramount for the aircraft industry. So, they prevent catastrophic failure of jet engines in flight. They also help to increase the engine efficiency and longevity. Two major axes of TBC R&D today. So, people are trying to increase the manufacturing efficiency of TBCs and the longevity of the current YZ TBCs. And also, for example, we're trying to develop new TBC materials that can operate at temperatures higher than 1,300 degrees Celsius. And these both axes of research are present in our SurfTech consortium of the NRC. And if you like my presentation, if you enjoyed and you want to have more information about it, just by a nice coincidence, the paper version of this presentation was published in August 22nd. Basically, 2 weeks ago. It's a special issue of the Coatings Journal, Recent Developments of Thermal Barrier Coatings. The guest editor is Dr. Nicholas Curry, so he's a rising star in our thermal spray community. And this is a kind of open access journal. It means that if you click on this website, we'll be able to download the paper for free. And at the end of my presentation, Vesna is going to send you via email this web link. So if you want to download a copy of that paper, if you want to better understand my presentation of today, you'll be able to get it. And acknowledgement, so the NRC technical officers, so David Delagra for the movies that you saw today, so he was able to edit the movies, and for metallographic preparation of the TBC samples you saw, Karine Teberge for the SCM pictures, and Jean-Claude Tremblay for APS TBC manufacturing and for laser rig operation. And thank you very much, merci beaucoup, and I hope you have enjoyed my presentation.
Thank you very much, Dr. Lima. Absolutely wonderful talk.
Thank you.
I think that we have all learnt a lot. What I'd like to do now is open the floor for some questions, whether any questions have come in. And at this point in time, I'm looking at Vesna to see whether we do have any questions coming in.
Yes, Chris, we do.
Assisting us.
Would you like for me to read the questions, or did you want to?
Could you please read the questions, Vesna?
Yes. So we have a question from David. Does spallation occur at the bond coat, TBC, or substrate interface?
Basically, it can occur in different zones. But basically, for example, it can occur exactly at the TGO, in the middle of the TGO. So we have, for example, if I go back in here, okay, to this question here. Let me see if I go back very quickly. Okay. Let me see in here. Okay. Oh, it's right here. For example, this spallation can occur really here. I mean, you're going to have with time the formation of an oxide. It's called the thermal oxide. So the spallation can occur right here in the middle. It can occur also, for example, within here the YSD TBC, or can occur, for example, in between the TGO and the bond coat. But basically, okay, it can occur in different areas, but basically it's going to be around here, around the TGO. So depending on the residual stresses that you have in your coating, and depending on the TGO thickness, okay, you can have different areas of failure, but all they're going to be around this area here.
Thank you very much. Vesna, any other questions, please?
Yes, we do. We have a question. Can TBCs be used to protect furnace parts, high temperature nickel alloy base, furnace cycles ambient to approximately 1000 degrees Celsius, 3 to 4 times per hour?
Could you please?
I think the question is referring to a non-traditional aircraft application. I think it's referring to another application where a thermal barrier might be needed within a furnace environment.
Yes, for example, I mean, you can use TBCs in cars, in car engines, for example. It's another application of TBCs. So if you have any type of surface where you need to have a barrier, you have to basically to keep the heat or protect a surface against heat, a TBC can be employed. But basically the main application is for turbine engines, but it can be applied in other applications too. Why not?
Okay, let me carry on here. There's a question from Bruno. Hello, Dr. Lima. I work with zirconium boride coatings, which oxidize in operation and the crystal structure changes. Could you give some examples of the failure mechanisms associated with phase transformations and sintering?
Oh, yes. For example, if I can go in here, okay. So, I have just to move in here, so I have to go to my appendix, okay, to give you some of the mechanisms, okay. So basically, why the TBC temperature limit is 1300? One of the things you have, for example, you have calcium, magnesium, aluminum oxide. These are ash and sand, the airborne particles. Basically, they pass through the combustion chamber, they melt, and they stick on the TBC. It's a glassy phase. And they are basically fully molten at 1300 degrees Celsius. So when they reach this temperature, basically they penetrate into the engine, into the TBC. And therefore, for example, we have the YSD, the acidification agent. We have laws of strain tolerance because you have a glass inside the TBC, so you are cycling, turning on, turning off the engine, and therefore the TBC is losing that capacity of having strain tolerance, and you have the TBC spallation. Concerning phase transformations, for example, typically TBC is that after, for example, 1300 degrees Celsius, the T prime phase, so I'm going to be a little bit technical right now. So the T prime phase is going to transform into the regular tetragonal and the cubic phase. So when you have the regular tetragonal and when, for example, the temperature goes, for example, from operation temperature to room temperature, you have the formation of the monoclinic phase. When you have the monoclinic phase, you have a volume change. So the monoclinic phase, when you transform from tetragonal to monoclinic, you increase the size of the phase, right? So it's about 3 to 5% in volume. And therefore, for example, as ceramics, you have lack of plasticity, okay? The only way to release stress is in a microcracking. So if you have, for example, microcracking, what's going to happen is you have the loss of mechanical strength. So when you have any type of phase transformations in ceramics and at low temperatures, so the way to release stresses is via microcracking. And therefore, for example, you lose mechanical strength, and this leads to TBC spallation. Finally, for example, sintering. So the higher the temperature, the higher the sintering, and we're going to have YZ densification, so it's going to densify the YZ, and we're going to have a higher thermal conductivity for the TBC, so it means that the thermal barrier effectiveness is going to go down, and it leads to TBC spallation. So I hope I was able at least to reply or to address part of your question.
Another question, Rogerio. I'm going to paraphrase a long statement. Talk a little bit about bond coat development. And chemistry for bond coats.
Okay, so I can tell you right now, for example, it's one of the things that's very, very interesting. Bond coat is fundamental for the survival of the TBCs. So you have to develop bond coats that are going to operate at higher and higher temperatures without having a major oxidation in the coating. So if you can, basically the bond coats, the maximum limit they are operating right now is about 1,100 degrees Celsius. At temperatures higher than 1,100 degrees Celsius, basically the oxidation becomes, I'll say, uncontrolled. And therefore, you tend to form here a kind of complex oxide here between the bond coat and the TBC. And imagine, for example, that growth is jacking up the TBC. So it's growing, and the TBC spalls. So any type, for example, high temperature alloys, okay, high entropy alloys. So alloys that can be highly stable at very high temperature are of high interest in the TBC area. And also, for example, if you can try to deposit this type of alloys, causing a very low oxidation of the bond coat, this is really, really, really important. So, and mainly right now, when you are talking about development of suspension plasma spray TBCs to try to replace EBPVD TBCs in turbine blades, the development of new compositions for bond coat is really, really important. And I can tell you that there are many confidential issues regarding that, but it's a very key aspect, okay, on TBC development. Another question:
how do you remove the coating in order to repair it?
Okay, basically to remove the TBC, the YZ TBC is easy. You can use a grit blaster or can use, for example, water jet, okay, in high pressure. You can remove the ceramic. This is easy. To remove the TBC, the bond coat is quite complex, so you need to use a chemical bath to attack, okay, the bond coat without attacking the substrate. It's a very complex and kind of nasty type of system.
David is asking a question about whether the TBC should be sprayed under nitrogen or vacuum conditions.
Okay, I would say, wow. The TBC, okay, basically I would say that you want, for the ceramic TBC, you want to create porosity, okay? So if you want to create porosity, I will not use vacuum. I would prefer to use, for example, regular air plasma spray. And one of the good things about using nitrogen is the fact that you generate a lot of enthalpy in that plasma. So it means that we're able to increase a lot the deposition efficiency of the TBC. And this is very, very important because we're reducing the production cost. So I would prefer to use, how can I say, in fact, in the NRC, the way we are spraying our benchmark TBCs, we are using a nitrogen plasma in that plasma spray. But I will not use vacuum to spray the ceramic TBC because you would tend to make a very, very dense coating. And you need to have that process to make a kind of Swiss cheese to give the TBC its capacity to withstand the cycling that you have, for example, when you operate in a turbine engine.
So Min has a question about the surface roughness.
Okay.
And let me paraphrase this question. are the coatings used in the as sprayed condition, or, expanding on this question, would any polishing of the surface give any aerodynamic benefits?
Yes, I mean, in some cases, yes. In some cases, for example, depending on the region, and mainly for the blades, okay, you are going to have, you may do some type of polishing to improve the aerodynamic performance of the blades. Yes, it's true. It's not mandatory, but it's done in some cases. It's right, to improve the aerodynamic performance of the surface. It's true.
David wants to know how many times you can refurbish a component. How many times can you remove the coating and put a new coating on?
That's a very good question. I mean, how can I say a turbine engine can last for 30 years? Yes, a turbine engine can last for 30 years. It means that, I mean, you have the turbine engine, you make brand new, and then you have the TBO, right? You overhaul everything, remove all the coatings that you have, and put it back in and start flying again. And then you reach the TBO, okay? You get the turbine again, disassemble, refurbish, and it's about 30 years. It's really amazing. So, for example, you can be born, you can get married, have a kid, and the same turbine is still flying. It's just amazing. It's a fantastic type of equipment.
So Amy has a question about the microstructure on slide 12. Okay. And she wants to talk about the porosity levels of the bond coats. What are the acceptable porosity levels on bond coats? And she's referring to slide 12.
Okay, so basically, as a kind of, let me see, as a kind of thumb rule, okay, people like to have porosity levels less than 5%. And
slide
why?
12.
Slide 12, exactly. Now I'm seeing here, right?
Yeah.
So slide 12. Okay, so basically, as a kind of thumb rule, people would prefer to have porosity of the bond coat less than 5%. And why? Because I mean that if it's less than 5%, you have less possibility of the oxidation of the pore. So basically, the air is going to come in, right? And if you do not oxide, okay, if you avoid oxidation of the pore, so we're not spilling the aluminum that's so precious for the bond coat. So typically it's less than 5%, and ideally, for example, the lower the better.
So I've got probably another 2 questions so that everyone knows where we're heading. So we'll be closing down in less than 5 minutes.
Okay.
Looking at this micrograph here, Kieran would like to know what drives sea mass infiltration. What is the driving force for sea mass infiltration throughout the TBC?
Capillarity effect, man. It's basically capillarity effect. It's right there. So basically, you're going to have here a glass material. Okay, if the temperature is high enough, and if the amount of material is high enough, it penetrates. Imagine, for example, if you have a TBC and you have an epoxy resin, right? So don't you see the epoxy getting into the TBC when you mount them? Okay, it's basically the same principle, capillarity effect, just like a sponge, it goes in. Okay, and in TBC you need to have the porosity in order to give the coating capacity to withstand thermal shock. And that's why, for example, because of the porosity, and you have a molten material over the TBC, it penetrates into the porosity, and we start to have the problems.
Okay, so we're going to get down to the final question here. Peter has a very interesting question, a very searching question. And then I'm going to ask you to have some closing comments, Rogerio. And then I'm going to ask Vesna to get ready to present that very final slide for the audience. Okay. So here's the question from Peter. What do you think, this is the $1 million question, what do you think are the knowledge gaps in TBC development? What do you think are the knowledge gaps in TBC development?
This is a very nice question, and it's when you look at the literature on TBCs, on the ceramic coatings, okay, basically the papers in general, they tend to show the same trend, okay, on the ceramic coatings. But when you look at the papers on bond coats, okay, the results can be totally different because you have so many effects happening in the bond coat. Sometimes, for example, a paper, you can see paper A and paper B, they have very, very different effects. So, and that's why, for example, we have a lot of information that we need to know. It means that we need to have more information about bond coats. It's a very, very important things because I mean that we are seeing different results from different authors. Some authors, for example, there is a big truism, okay, in thermal spray and TBCs that the VPS, the vacuum plasma spray, the vacuum plasma spray bond coats are the best ones. But there are different authors, including papers on the NRC, were showing that it's not necessarily the same. So that bond coat development, for me, is a kind of gap that you have to know more information.
Okay, thank you. We're drawing to a close here. I'm just wondering, Vesna, whether you can pull up my very last slide so we can close down. So this is one of many SEAM webinars which are going to be held over the coming years. I'd like to warn you or give you some advance notice that we'll be having a seminar on wear and corrosion from Professor Rehan Ahmed, and we'll also be having another presentation from Professor Sampath, and there are other people who are lined up. But with this very final slide being shown, I'd like us all to virtually applaud Professor Dr. Rogerio for his wonderful seminar, for navigating quite calmly a few IT glitches. Well done, a fantastic presentation, and I am sure that we've all learnt a lot. So for that very final thank you very much, Professor Dr. Rogerio Lima.
Professor Berso, thank you so much. I mean, I love to see these pictures. I mean, I had a wonderful time in Australia. I was so very well received. I love the MICE 2020. And I can show you, for example, I have some Australian things here with me. For example, can you see my Australian mug? Okay, the koala mug in here. Okay, I have here, for example, a boomerang. And I'm testing here in Canada. So depending on the angle you throw it and the direction of the wind, it comes back to you. It's really amazing. It's very nice to play with boomerangs. And here, for example, I have Australian soil. Okay, it's a stone from Guanamara Beach. Okay, here with me. So I mean, I had a very nice time in Australia, and I look forward to visit you guys again. So thank you very much for this opportunity to share this knowledge with you. I mean, the objective is to create a presentation for your students, and I hope they learn something new today.
Good. Thank you very much. Let us now close this seminar. Thank you very much.